All right, so what I'd really like to get to here today is buoyancy. But before we can talk about buoyancy, maybe we should talk a little bit about pressure and what it is and what's going on here. So first I'm going to talk about what pressure is here. Then I'll talk about what you probably remember about pressure, the force divided by the area sort of thing. And then we'll go to buoyancy and how all this pressure stuff relates to buoyancy. So what we're going to do here is we're going to look at sort of a fluid column. So we're going to have some fluid and then an object down here, then some fluid above it. So we're going to be at a depth D. All right. So we want to look at that. And we're going to kind of make an assumption about the pressure being the pressure at a point, at a depth D is the weight of the water column above it. That is the weight of this cylinder, right? This is our object. This is our water column. And there's one more thing we have to add here, which is plus the atmospheric pressure. So we've got some atmospheric pressure, which is 101 kilopascals or something like that. And so, you're just walking around right now, and that's the pressure on you, something around 101 kilopascals. And then we're adding more pressure as we go down. So this ball is down here. Above it is a water column of depth D and area A. So it has a pressure based on that. That pressure is the pressure at a depth D. That's my pressure. We'll call that the absolute pressure, which is equal to the atmospheric pressure which is about 14.7 pounds per square inch, or about 101 kilopascals, depending on how you're measuring it, imperial or metric, plus the density of the water, fluid density, times the volume of the water column, column volume, times the gravitational acceleration. G is equal to 32.2 feet per second squared is equal to 9.81 meters per second squared, that thing. So that's what we're going to use as our pressure. So the pressure basically linearly decreases with volume or depth. So if this is your depth, then your pressure basically starts at 14.6, 14.7 psi, just increases linearly as you go below the surface of the water. That's it. So if you know the water density, then you can always find that pressure. If you look at real water columns, it's very, very close. It's not exactly true, but it's very, very close. Finally, we normally measure the pressure with the gauge pressure. So if you take your tire gauge and you look at what the pressure in your tire is, it's reading what's called the gauge pressure. That's why it's called the gauge pressure, because you're reading it with a gauge. This gauge is a relative pressure. And what I mean by relative pressure is it is the difference between the atmospheric pressure and the absolute pressure. So what you really care about, and we'll talk about why in a second, but what you really care about is that gauge pressure, so that whatever it is, 35 psi difference between outside and inside your tire, that's what keeps it inflated, is that pressure difference. So that if the pressure outside decreases, then you're going to want to let some air out of your tires so that you have a similar pressure on either side, so your tires don't pop. And similarly, if the pressure outside increases, you might want to add in more air to your tires so that they don't deflate and you don't end up with a flat. Okay, so that is what pressure is. It's basically this buildup of the column above here. We could also talk about it in terms of something else like the energy density. It is the energy density of the water. But we haven't talked about energy, so it's a little early to talk about that. Well, we talked a little bit about it, but it might be a little bit early to talk about that. All right, so that is the pressure. Next, we'll go on to talking about forces from pressure. Then we'll come back to talking about the buoyancy, basically because of the pressure difference. Okay, bye now.